Welcome, dear learners. Today I want us to look at wave basics. Let's start by looking at the objectives of this lesson. By the end of the lesson, you should be able to describe what is meant by wave motion as illustrated by vibrations in ropes, springs, and by experiments using water waves. Name and identify longitudinal and transverse waves and distinguish between the two. Define and draw wavefronts. State what is meant by wave speed, frequency, wavelength, and amplitude. And identify and draw a crest, amplitude, wavelength in a wave diagram. And be able to use this equation: V is equals to frequency of speed is equals to frequency times wavelength. Let's discuss the basics, the general information about waves. What are waves? Waves can be described as oscillations or vibrations about a rest position. For example, sound waves cause air particles to vibrate back and forth. Ripples like as shown in this diagram cause water particles to vibrate up and down. So when we talk about waves, it is caused by disturbances. The disturbances result in oscillation or movement of particles. Then in that way, waves are generated. Waves transfer energy between points without transferring matter. The matter generally doesn't move, is not transported. It is only the energy that is being transferred by the wave. When a wave travels between 2 points, no matter actually travels with it. The points on the wave simply vibrate back and forth about a fixed position, or it vibrates up and down. So like in the example here that is shown here, when the energy is traveling this direction shown by the arrow, so this dark is going to be moving up and down. So this arrow shows the motion of the dark, which it moves up and down in a fixed position. It doesn't travel with the energy. The energy is going to pass while the dark is still moving up and down in a fixed position. So in that way, you should note that waves do not transfer matter, but transfer energy. All right, so you see this animation, the wave, the dark is moving up and down, and the energy is being transferred. So the energy is moving with the wave. So let's take the wave as it appears. So let's start with the wave here. So it is moving, you see, it to this direction. Yes, in that way, then we can tell that wave doesn't transport matter because the dark has not been transferred, didn't move with the wave. Longitudinal and transverse waves. Waves can exist as one of two main types. We have transverse wave and we also have longitudinal wave. So we want to discuss these two types of waves. Let's start with the transverse wave. A transverse wave is one in which the vibrations of particles are at right angles. So please note, the vibrations are at right angles to the direction in which the energy of the wave travels. They are at right angles, meaning they are perpendicular. They are at 90 degrees to the direction at which the energy travels, to which the direction of the energy travel. So here, this is how we can form a transverse wave. Transverse waves can be formed by using a rope. So here we have a rope. The rope has, one end of the rope has been fixed in this position, and then this other end is made to move up and down. So it moves up and down. As you move the rope up and down, we are going to form this transverse wave. So this is a transverse wave. So what do we mean when we say the vibrations of particles are at right angles to the direction in which the energy of the wave travel? So let's look at this one. So here we have the direction of vibrations, which is the vibrations by the hand. These are the arrow shows that this arrow shows the direction of vibrations. So it is up and down. And then we have the direction of the energy. So this is the direction of the energy travel. So as you move it up and down, energy moves from this other end to the last other end. Now you can see these two are at 90 degrees. These two are at 90 degrees. So that is why we say for a transverse wave, the points along the wave vibrate at 90 degrees to the direction in which the wave is moving, or to the direction of the energy transfer. Examples of transverse wave could be ripples on the surface of water, vibrations in a guitar, electromagnetic waves. We are yet to talk more about electromagnetic waves. So those are examples, common examples of transverse waves. And then let's look at longitudinal waves. What are longitudinal waves? Longitudinal wave is one in which the vibrations of the particles are parallel now. Remember in the other, with transverse waves, we say they are at 90 degrees. Now they are parallel, meaning they are facing the same direction. So they are parallel. The energy, they are parallel to the direction in which the energy of the wave travels. So here, when you define a wave, you should talk about in terms of vibrations and also terms of energy of the wave travel. So it is either they are parallel or they are longitudinal. So transverse and longitudinal, and then, sorry for that disturbance, let us continue. I was saying transverse waves are what? We say transverse waves, the vibrations and the energy, the direction of energy travel are perpendicular, while in the longitudinal waves, they are parallel. Okay, so this is an animation to show how transverse waves can be generated using a slinky spring. So what is happening here? You are moving the hand up and backward and forward. So you move this hand forward and back, forward and back. So what happens here? The particles are going to be moving forward and backward. So if we would say we take just one portion of the spring and just notice how it moves, you will find that it will move forward and then backward. It will move forward, backward repeatedly. So that is if the hand was moved forward and backward repeatedly. So now here you can see that this is the particle motion also. This is the vibration. This arrow shows the direction of vibration. So this is vibrations. So this shows the direction of vibrations. And then the direction of energy travel is shown by this arrow, which is here. This green arrow, it shows the direction. So now you can see that these two are parallel. So we have this showing the vibration and also this showing the energy. And now you can tell that these two are parallel. So that is why we say when we define a longitudinal wave, it is when the vibrations of the particles are parallel to the direction in which the energy of the wave travels. So here, demonstrating a longitudinal waves show areas of compressions and reflections. So when it was being, when the slinky spring is being pushed forward and backward, we are going to get compressions and reflections. What are compressions? Compressions are the regions of high pressure due to particles being close together. The particles come close together and then we call that a compression. So if you can look at this region here, so this region is a region of compression because the particles, or the coils in this case, because it's a spring, the coils are close together. So there is high pressure there. And then there are reflections. So these are regions of low pressure due to particles being spread apart. So here, if you look at this one now, those are regions of where there is low pressure and the particles are, or in this case, are the are the coals. They are further apart. So even if you come back here, you can see this which moves with that part that seems to be moving, that shows the compression. And then so we have compressions and reflections until it reaches the end part. Okay, so here in the diagram, the compressions move from the left to the right, yes, to the right, and energy is transferred from the left to the right. So like in this case, energy transfers is moving to this direction, and then the compressions also are moving the same directions, from the left to the right. The movement of coils of the slinky and the energy are parallel. However, none of the particles are transported along the longitudinal wave. So as we have said that waves do not transport matter but only transport energy. Instead, they move backward and forward as the wave is transmitted through the medium. So even in air particles, so we said, or maybe let's start by looking at examples of longitudinal waves. The common example is sound, and then we have ultrasound waves, P-type earthquake waves. So sound waves, when sound is moving from a source to the ear of a human being, so let's say this is the ear, sorry, when the sound is moving from this source to the ear, so there are air particles in between the sound, the source of the sound, and then the ear. So what is going to be happening, the particles are going to be compressed, the air particles compressed. There will be some compressions and reflections of the air particles, but you should note that it doesn't mean that the air particles go with the sound energy. They only compress at some region, and then there are also some reflections at other regions. So we're going to look at animations that shows that. All right, now let's look at the parts of the wave. Let's start with the transverse wave. So parts of the wave, the transverse wave has got the peak, the amplitude, the wavelength, the throw, and the rest position. So let's define these parts of the wave. So let's start with the rest position. The rest position is the undisturbed position of the particles of field when they are not vibrating. So we normally, in a transverse wave, we normally draw the line through the center of the wave, through the middle of the wave. We say that is the rest position. So that's when the wave has not been disturbed. For example, if we are talking about water waves, so that's the general level of the water waves. And then when you, so the general level of the water in the pond. And then when you start forming waves, there will be some upper regions, which are the peaks, and then the lower ones, which are the troughs. So, and then let's look at the displacement. What is a displacement? This is the distance that a certain point in the medium has moved from its rest position. And then the peak. The peak is the highest point above the rest position. So this is the peak, as you can see there, shown in the diagram. It's the peak, it's the highest position. Then we have the throw, which is the lowest position of the wave. All right. And then we have the amplitude. The amplitude is the maximum displacement of a point of a wave from its rest position. So this here we can see the amplitude. If we are measuring an amplitude normally from the rest position to the peak, or from the rest position through to the trough. So that is where we find the amplitude. So that's it is a distance, the maximum distance or displacement of a point of a wave from its rest position. So here we have amplitude. So this one is still an amplitude, and this one is another amplitude. So those shows different amplitude. Wavelength. What is a wavelength? A wavelength is the distance covered by a full cycle of a wave, usually measured from peak to peak. So as shown in the diagram. So this is the wavelength. So we measure from peak to peak. So you need to be careful in the exam. You are normally learners, you find that they show the wavelength here. So no, you have to first identify the peak or the throw. So here we can show it here. So we have, this is the highest point, these are the highest point. Then now we can draw the wavelength. So this is the wavelength. Even here, when we are using the peaks, you should make sure that you throw it at the peak, between two peaks, not just to draw it here. So this is not the wavelength. So this one is very incorrect. Okay, so, or we can also draw the wavelength from where the wave starts, because one wave moves from this, so this shows one wave. So this is a complete cycle. So now, when we are saying wavelength, that means the length of a wave. So that tells you that the wavelength drawn from peak to peak or trough to trough is the same as this one. So from measuring from where the wave starts. So the wave starts here and it ends here. So this line is equals to the wavelength. And also this one, so let me use a different color. So also this one from here to here is another wavelength. So I'm still drawing the wavelength here. So you can draw the wavelength at any region where you would like. So like if you look at this diagram, so this shows the wavelength. Actually the wavelength, you can also define it as the distance between two similar successive points. Two similar successive points. So if we have taken a trough, a crest, we are going to take another crest here. And then we draw, this is the wavelength. If we take a trough, we take this trough and this trough, see, and the upper part is the peak. So we can also draw the wavelength from where the wave starts here to where it ends. So one wave here. So this is one wave. So then this is a one wavelength. So here, how many waves that we have here? We have one, that's one wave, and then 2, 3, 4, 5, 6. So we have 6 waves here. That is why if we were drawing wavelengths, we could have 6 wavelengths. So this is 1, 2, 3, 4, 5, 6. All right, so there are 6 waves here. Okay, let us continue. Then we have a time period T. What is a period? A period is the time taken for a full cycle of the wave, usually measured from the peak to peak or trough to trough. Period is measured in seconds. A period of 2 seconds means that the time for one complete vibration is 2 seconds, or the time the time taken for one complete wave to pass a point is 2 seconds. So when we are talking about periods, that's the time taken by one complete wave to form, or taken by one complete wave to pass a certain point. So if we say it is 2 seconds, the period, we mean that wave has taken 2 seconds to form. Okay, let me go back to this diagram. So if I were to have a wave, one wave like this, so let me just draw one wave. So this is one wave. So if this one wave forms in 2 seconds, then we are going to say the period we use the capital letter T. Period is equal to 2 seconds. So please note that in physics you have to use the right symbols for the different quantities. Here we are talking about period. Period, we do not use P, we use T, capital letter T, because if it is small letter T, then it means another thing, it means time. So period here is 2 seconds. So it means it has taken 2 seconds to generate this wave, or it has taken 2 seconds for a certain point of this wave to pass, for a complete wave to pass a certain point. And then we have another quantity which is called frequency. We use the small letter f to represent frequency. Then what is frequency? Frequency is the number of waves passing a point each second. The number of waves passing a point per second. Frequency is measured in hertz. So that is the unit of frequency. Or we use this Hz to write this unit symbol. A frequency of 50 hertz means there are 50 vibrations every second. There are 50 complete waves passing a point every second. Then we say that is 50 hertz. If we have 2 hertz, so if we have 2 hertz, what does it mean? It means there are 2 waves passing a point in 1 second. So you should note that frequency is always the number of waves per second. The number of waves per second, that is frequency. When time, it is just the general time, period. It is just the general time taken by a wave to complete 1 cycle. In the following diagram, let's look at this example. In the following diagram, the wave moves from left to right and then stop. The motion of the wave lasts for 2 seconds. Okay, so here we have a wave that moves from the left to the right, and it takes 2 seconds for this wave to form. All right, now let's look at the question. So let's calculate the amplitude here. What is the amplitude of this? So the amplitude is very simple. We say the amplitude, it is the maximum displacement of a point measured from the from the rest position, or it is the distance between the rest position and the trough, or the rest position and the crest. So this is the amplitude. The amplitude, it is 0.4 meters. So this is the distance, or this distance from here to here. So this distance is 0.4 meters, or from here to here. So that is the amplitude. So the amplitude is 0.4 meters, or we can say it is 40 centimeters. And then the wavelength. Wavelength, it is the distance between 2 successive similar successive points, or it is measured from trough to trough, or from crest to crest, or from the start of a point to start of a wave to the end of the wave. So if we say we measure from the start of the wave, so the wave starts here and it ends here, and then what is this distance? Let me use a different color. What is this distance shown here? I can't draw a straight line. So this distance, so that one, it is 2 meters. So then it tells us that the wavelength of this wave is 2 meters. So please note that the symbol for wavelength is this one. We use this symbol lambda to represent a wavelength. And then frequency. What is frequency? We said frequency is the number of waves passing a point every second. Number of waves passing a point every second. So this gives us a general formula to find frequency. Like when we want to calculate frequency, we're going to say the number of waves over time. The number of waves over time. So how many waves were formed here? So we have 1, 2. So 2 waves form in how many seconds? So they told us 2 waves form in 2 seconds. So then the frequency here is going to be 2 over 2 over 2, which gives us, so it's 2 waves over 2 seconds. So that is going to give us 1 wave per second. So when we have this 1 wave per second, so that tells us we do not write it like this, 1 wave per second, but we convert it and write it as hertz. So that is 1 hertz. Another example, 2 water waves are generated in 4 seconds. We have 2 water waves generated in 4 seconds. Calculate the frequency of the wave. Frequency is the number of waves over the time taken. We have 2 waves over 4 seconds. We're going to get what? 0.5 waves per second. And if we have waves, so we have just said waves per second, we do not write it like this, but we are going to write it as what? Hertz. So that is 0.5 hertz. Okay. So another question, a graph of displacement against distance for a wave passing through water is given below. What is the wavelength of the wave? Let us look at this diagram. So here we have a diagram. We want to find the displacement, the wavelength of this wave. The wavelength of this wave. Wavelength, we have said it can be measured from the start of a wave to where it ends. And also it can be measured from the peak to peak, or from crest to trough to trough. So you remember that the peak is also the crest. I don't know if I had mentioned that. What is the amplitude of the wave? So we want to solve this one. So here is the solution. The wavelength is the distance covered by a full cycle of the wave, usually measured from peak to peak or trough to trough. The distance between these two peaks here, as shown in this by this arrow here, is going to be what? Is what? 8 meters. 8 meters. The wavelength of the wave, therefore, is 8 meters. So let me go back here. So you should be here. You need to be very careful of the divisions here, or the divisions here. So we have 0, and this one is 2, 4, 6, 8. So you see that is 8. So this is the distance, which is 8 meters. And then we have 10 here, 12, 14, 16, 18, 20, 22, 24. So you should be very careful here. Most learners would say the wavelength is 10 because it is what they are seeing here. They can see that number only, and then they think it is 10, and then 10 is incorrect. Amplitude is the maximum displacement. So another way, we're asked to find the amplitude. Amplitude is the maximum displacement of a point of a wave from its rest position. So here we are going to find that the amplitude is 2.5 millimeters. So which is the half of 5. So you do not just take 5. So you can see the amplitude is halfway between that. So that is 2.5 millimeters. So if mechanical and electromagnetic waves, mechanical waves cause oscillation of particles in a solution, liquid or gas, and must have a medium to travel through. They cannot pass through a vacuum. We call those mechanical waves. And electromagnetic waves cause oscillation in electrical and magnetic fields and can travel through a vacuum. Let us look at wave speed. The speed of wave is related to its frequency, meaning the frequency of the wave, and the wavelength of the wave. So therefore we have this equation. So please, ladies and gentlemen, you note this equation. Speed is equals to frequency times wavelength. So we've said we use this symbol to represent wavelength. V is the speed, F is the frequency, and then a lambda is the wavelength measured in meters. Frequency is measured in hertz, and speed is measured in meters per second. So we should use the correct SI unit to find frequency or to find any of those. So you can rearrange, you can use this triangle here to rearrange the equation and find, depending on what you have been asked to calculate in the exam situation. So when you are using this triangle, like if you want to find V, we are going to say V is equals to frequency times wavelength. So here this is times and this is divide. So this one is like we are dividing. All right. So if you want to find frequency, what you do, you close frequency, and then frequency is going to be speed over wavelength, and so forth. All waves including sound waves, and electromagnetic waves, follow this equation. It should be noted that some particular waves have their own specific speeds. So for example, the speed of light and all the electromagnetic spectrum in a vacuum is 3 times 10 to the power 8 meters per second, which is 300 million meters per second. That's the speed of light in a vacuum. But the speed of sound in air is 340 meters per second. So it's somewhere around 340 meters per second. Let's look at this example. What is the speed of a wave that has a frequency of 50 hertz and a wavelength of 6 meters? What is the speed? So speed is going to be frequency times wavelength. So you get a mark for giving the equation, and then you substitute, which is 50 times 6, and then you're going to get 300 meters per second. What is the speed of water wave that has a frequency of 0.5 hertz and a wavelength of 3 meters? Okay, so I didn't write the solution for this one, but you can just pause the video and work on it. What is the speed of a wave that has a frequency of 0.5 meters and a wavelength of 3 meters? So you can calculate speed is equal to frequency times wavelength, which is 0.5 times 3, and then what are we going to get here? We're going to get a 1.5 meters per second. So this wave is traveling 1.5 meters in a second. That is the speed. Wave period and wave speed. So this time period, the time period of a wave can be calculated using this equation. So you can use this equation to play around frequency and period. Like time of a period or time period, or the period is equal to 1 over frequency. Where, yes, 1 over frequency. So you can use this equation. Also, if you want to find f, you can make f the subject of the formula. You're going to find that frequency is equal to 1 over period. All right. So calculate the time period of a wave with a frequency of 50 hertz. What is the period that is taken by this wave? So you can calculate it like that. So 1 over f, which is 1 over 50, and then you get 0.02 seconds. Here's a task. Calculate the time period of a wave with a frequency of 400 hertz. So please pause the video and work on this one. All right, let us continue. So here what we get, we want to find period. So period is equal to 1 over frequency, and then what have we have 1 over 400, and then what do we get? 1 over 400, we are going to get 0.0025 seconds. So that is the frequency, that is the period of this wave. Wavefronts. Wavefronts are usually a way of picturing waves. Each wavefront is used to represent a single wave. Wavefront may be drawn to represent a certain point of a wave. For example, the crest of a wave in a ripple tank can be thought of as wavefront. So when we are drawing wavefront, this is a simpler way of representing waves. So what we do, we take the similar points of the wave, and then we draw those points. You use lines to represent those points. So we are going to get what? We're going to get wavefronts. So this diagram shows a wave drawn as a series of wavefronts. So here is a wave. This could be a longitudinal wave or even a transverse wave. So we are taking, so if maybe we were having waves that are formed, water waves formed, maybe using a straight ruler, a straight ruler. So those waves are going to be moving from one end to the other end. So now, instead of drawing those waves like this, we are going to take draw the wavefront. So we can decide maybe the wavefronts are the peaks. So we take the peaks, which are the crest. So this the crest, the second crest, the second crest, the second crest. So now, then we draw those ones as just lines, as shown here in this diagram. So those are the lines here in this case will be representing the crest or the peaks. But if you like, you can make the lines to represent the throw, so it doesn't matter. So you're just representing similar points of the diagram, also of the wave. And then we come up with wave fronts. So which is what you see there. So this one is going to be, it's going to make it easier for us when we are drawing, as we are making some more experiments and calculations with waves. All right, so here is a wave front that shows a longitudinal wave, which here we have the compressions, and here we have reflections. So we use wave fronts. So we call these lines, we call them wave fronts. Now let's look at a ripple tank. So the ripple tank is used to study water waves. So the study of water waves makes it to be easy to generalize on what happens in the other waves, like light waves or in other electromagnetic waves. The behavior of water can be observed by using a ripple tank. This instrument consists of, it has got a transparent tray that contains water. So here we have this tray, and it contains water. We have a light source here. You see this lamp. So that light source is above the tray. It shines over the water, and then that is going to make the waves that are formed here. So here we have a tray. So in the tray we put water of small amount so that it is just shallow, like 5 millimeter deep to 1 centimeter. 5 millimeter to 1 centimeter depth of the water. So the light, when it shines over the tray, there are going to be waves forming on the water. Sorry, the water that forms. Let me start afresh. So we generate the waves, and then to see those waves, we have to have this, what we call a white screen, down there at the bottom or below the tray. So the white screen is going to show the reflection of the waves that have been formed, because there is light above here. So when it ikhanyisa kwale tray, stabe sesekubonakala lama waves la formshekako la kule tray, atawubonakala ngakuphi manje, sitawubona la ngaphansi. So it is easier to look at them at the bottom. So, and then that one is going to make it easier even for us to trace and also to draw them. So let me just erase everything here. So, and then we have an electric motor. So here is this motor. This motor, this is the motor. And then the motor causes this to vibrate. It could be a flat, a straight edge like a ruler, a small plank like a ruler that is going to be vibrating, so to form straight waves. Or if we want to use to form circular waves, we are going to see how we form circular waves. So if we want to form circular waves, we are going to put a small ball instead of the bar. So here we have a bar to form straight waves, but if we want to form a circular waves, we use a ball. So it's just a ball like this. So the ball here, so this is the ball. So the ball is going to be caused to vibrate by the motor, and then it dips on and touches the surface of the water in the tray, and then waves are going to be formed. Or if we are using the bar, which we already have here in this ripple tank, so this one is going to give us straight waves. So please make sure you understand how we use a ripple tank. So there is another instrument here that we didn't put here. So the instrument is called, what do we call it? We call it A stroboscope. So I will show the stroboscope later, but it is used to view. It's not part of the ripple tank here. You just hold it with your hand, and then bese so ubuka ngayo mawufuna ukubuka lama waves pattern that are formed on the screen. So you can even do without it, especially if you are working in a darker room and then this light shine. You have this light, so atawubonakala kahle lama reflections of the waves latawubonakala lapha ngaphasi kule screen. All right. So maybe let me just repeat myself of what I've said about a ripple tank, because I want you to understand very well what a ripple tank has. So a ripple tank, it contains of a transparent tray. So the transparent tray has got water of about 5 millimeter to 1 centimeter yes, depth of the water. And then we have a light source above the tray. So the light source shines over the water so that a reflection of whatever happens in the tray is seen at the bottom, is seen on the white screen. And then we also have an electric motor which is used to generate continuous ripples. So it has got it's either we put a bar that gives straight ripples of if it touches the water, or we use a circular wave. We use a small ball which gives straight circular waves when it touches the water surface. So here, it's what happens. Images of circular ripples as seen on the screen below the tray. So here, I don't know if you will be seeing clear. So here we have the tray, and then we are forming circular waves. So we have a small ball. Maybe it's so you can see that small thing here. So that's the small ball, and it is touching the water surface, and then we are looking at the what? We are looking at the screen. So the screen below the ripple tank. So you will see these circular waves that are formed. So you will see these circular waves that are formed here on the screen. All right. So this is just another diagram to show. The frequency of the waves is determined by the speed of the motor. So if the motor is vibrating faster, then there will be more waves forming per second. And if it is slow, then there are fewer waves forming per second. All right. So yeah, that is the ripple tank. So we will be using the ripple tank to study the reflection, refraction, and diffraction of water waves. So here I just wanted to know how the ripple tank is used. So I didn't show circular waves, straight waves, because I think straight waves are just clear because they are just formed by this bar. All right. Oh, so this is the end. Thank you very much.